Yes? Okay. So, next presentation will be delivered by Mara Volpi from University of Namur, and she will speak on the stability of 3D planetary system configurations.
Thank you. I guess it's not changing the slides.
What is that?
All this is recorded, right?
This is not the best remark in order to let the things work.
I say it because it will be also recorded.
Sì, questo sì, se ve lo faccio portare.
No, aspetta.
Ok.
Sorry for the technical issues. So, good afternoon everyone. I'm Mara Volpi and I'm currently studying for my PhD at the University of Namur under the supervision of Anne-Sophie Libert. And today I'm going to talk to you about 3D planetary system configurations. The motivation that lies behind this work is that astronomical exploration are finding new and new exoplanets every day. Actually, I had to update the data from yesterday. But one of the main focus for present and future missions, apart from discovering always new generic exoplanets, is going to be to find Earth-like planets. And in order to do that, it is key to know to have a better knowledge of the structure of the exoplanetary systems in order to evaluate the chance that Earth-like planets are hiding themselves, for example, in the inner parts of these systems. We're going to focus our attention on systems detected by radial velocity method, which is very effective in detecting giant planetary systems, but has one big fault. It gives no information about the inclinations of the planets, both the mutual inclination between the planets and the inclination of the orbital plane with respect to the line of sight, which in particular means that we have only knowledge of the minimal masses of the planets. So our goal is to identify values of the mutual inclination between the planets that are compatible with the stability of the system. We're going to do this in this framework. In particular, let me stress 2 points. The first one being that as we need to choose a reference plane, it seemed wise to choose a constant one. And in this case, as we are going to consider 2 planet systems and only gravitational forces, the total angular momentum vector is a constant one, and therefore defines the orthogonal plane to be a constant one, which is the Laplace plane. And the second point is that we're going to consider only systems that are far from mean-motion resonances. The combination of these 2 things allows us to reduce our system to only 2 degrees of freedom. And therefore, the Hamiltonian that we're going to consider is this first order in the masses secular Hamiltonian, which is developed in the heliocentric canonical Poincare variables and in this parameter D2, which is the angular momentum deficit that measures the difference between the angular total momentum of the system and the one that the system would have if all the orbits were circular and coplanar. As we are going to talk about 3D configurations, let me recall the Lidov-Kozai resonance. It is a protective mechanism for highly inclined systems that typically appears around 40 degrees, even if the precise value depends on the characteristic of the systems. And in the Laplace plane, so the plane that we are going to use, the presence of the Lidov-Kozai resonance, it is indicated by the libration of the argument of the pericenter of the inner planet, of omega-1, around the values of 90 and minus 90 degrees, giving us this typical plot. So, to study this problem, we took a reference study of Libert Tsiganis of 2009, in which the authors explored the possibility for 5 extrasolar systems to be in 3D configurations, and in particular to be in a Lidov-Kozai resonance state. What they did was they considered the full problem and integrated that numerically. Obviously, our tool is completely different, as we have a secular approximation of the Hamiltonian, and therefore we ask ourselves 2 questions. The first one is that if it is accurate enough to perform a parametric study of the possible 3D configurations, and the second one, if it is effective enough to detect if the Lidov-Kozai resonant regions. In the reference study, the authors chose particular values for both the orbital plane inclination and the mutual inclination between the planets. And by comparison, we saw that our tool was working. And therefore, we decided to put the parametric study a little bit further. Therefore, obviously, we took the same 5 exosystems, and we decided to keep fixed the parameters that come directly from the detection via radial velocity method, and to change the parameters that are known. So the mutual inclination, and the inclination of the orbital planes. In principle, they could be different, but we decided to keep them equal to each other. And I would like to stress the fact that changing the orbital plane's inclination, we are changing the masses by the same multiplying factor. Let me introduce now HD 12661, who is going to be going to serve as an example for all the other parameters. All the colorful plots that we are going to see from now on have on the x-axis the mutual inclination, and on the y-axis the inclination of the orbital planes, meaning that if we follow an horizontal line, we have fixed the masses of the planets, and what we are doing is that increasing the mutual inclination between the planets gradually. On top, we have plotted the maximal excursion of the argument of the pericenter of the inner planet. As we said, in the Laplace plane, the presence of the Lidov-Kozai resonance is indicated by the libration of this angle. And therefore, we see that in the yellow part is where the angle librates, and in the purple ones, circulates, sorry, and in the purple ones is there where the angle librates. On the bottom, we plotted the maximal value assumed by the eccentricity of the inner planet. It is not a chaos indicator per se, by any means, but it has been proven in the past that to very low values of this parameter correspond stable orbits, and to very high values of this parameter correspond chaotic orbits. So it was a sort of partial check of our results. Obviously, we wanted to have a real check of the results and their reliability, and therefore we compared our results with the results coming from the M-body simulation of the full problem provided by Arnaud Rosin of our team, and this is what we have found. So, as we have found the island of libration with the secular approximation, it has been found the same island of libration with the N-body code. So what we see is that the secular approximation is in agreement with the N-body code up to very high mutual inclinations, which is what actually surprised us. This value of 80 degrees actually comes from the fact that it is the point in which the preservation of the energy starts worsening, and therefore we do not consider our results to be reliable. Now, we have seen that our tool has correctly indicated the libration, the island of libration that we expected. So let's see if it reads correctly the change in dynamics that increasing the mutual inclination provides. In order to visualize the change in dynamics, we are going to use this representative plane, which basically is on which basically we project the points of the motion for which the argument of the pericenter of the inner planet and of the outer planet assume the values of 90 or minus 90 degrees. And therefore, we want to have all the 4 possible couples of these two. It is not a phase space by any means. It is not a surface of section, but once we have plotted the level of course of the Hamiltonian, it's going to give a really nice visualization of the dynamics. On the x-axis, there is the eccentricity of the inner planet multiplied by the sinus of omega-1, and on the y-axis, there is the eccentricity of the second planet multiplied by the sinus of omega-2. So if you see negative values associated to the eccentricity, everything is fine, everything is under control. So we started with a small mutual inclination, and what we see is that in the center we have an equilibrium which is stable and corresponds to circular orbits, meaning that if we start with circular orbits, we are going to keep having circular orbits along the evolution of the system. As we expected, the argument of the pericenter of the inner planet is circulating, and we can see it even by the fact that the 4 points in which the motion intersects the plane are in the 4 quadrants of the plane. As we let the mutual inclination get higher values, what we see is that the center of the point of equilibrium that was in the center and that was stable becomes unstable. And what we see is that the center, the equilibrium point that was in the center, bifurcates into stable equilibrium. This does not affect our motion yet, because our initial conditions are such that we are not interested in this island anymore. But once we raise the mutual inclination again, what we see is that we are exactly inside the stable equilibrium given by the Lidov-Kozai resonance, and we see it in the same way, but in different ways at the same time, because in here we have the argument of the pericenter of the inner planet, which is librating around -90s, and in here we have the 4 points that now are only in 1/2 of the plane. So let's thank HD 12661 for its service, and let's see what happened with all the other systems. So basically what we had is that the comparison with the simulation of the n-body code was pretty good with all the systems, except for this one that has shown, for which our results are not reliable at all, because it has shown a worsening of the preservation of the energy for very low values of the mutual inclinations, and therefore let's not take into account. So just to wrap it up, we have shown that the circular approximation of the Hamiltonian that we have used is accurate enough to perform a 3D parametric study of the 3D configurations, and it is effective in determining the Lidov-Kozai resonance regions. We have seen that, as for our circular Hamiltonian, all the 5 systems could be in regular 3D configurations, in most cases up to very high values of the mutual inclination in mute, and in some cases even up to 75 or 80 degrees, which is quite impressive. As at the end, we have shown that most of the systems are compatible with significant Lidov-Kozai resonance regions, which is not news, because it was always already noted by Libera and Tsiganis in 2010. But it is notable that we managed to find the same result with the circular approximation. Perspective for this work are to extend the study to a larger set in the 2-planet system population, because obviously 5 examples cannot be enough. And secondly, speaking about the stability, we would like to study the stability of the systems through our tool of the circular Hamiltonian approximation, including chaos detectors. Because what we have seen is that the Lidov-Kozai region is stable, we can't say anything about the rest. And actually this is work in progress, and we are working for adding the chaos detector in the implementation of our tool. And with this, I thank you for your attention.
Questions?
Could you give us a few more details about how you produce the secular Hamiltonian, so up to what, let's say, order in the masses and eccentricity?
So this is a first order in the masses approximation. And as for the eccentricity, thank you for the question, because I forgot to say, it's up to 12 order in the eccentricity.
So it's fully non-linear, essentially, right? And what are the masses of the true systems?
I don't remember the exact values. I have the
Order, I mean, they are Jupiter-like or?
yeah, Jupiter-like.
Another question? Comment? Okay, let's thank the speaker again.